The Kathmandu Valley sits at the base of the Himalayas. Thick smog regularly rolls over this dense urban terrain, settling heavily into the basin. This 3D topographical map shows the valley's geological structure. High mountain ridges form a strict physical bowl, actively trapping pollutants and blocking wind currents from dispersing them. Looking closer at the data on this map, we see PM 2.5 levels reach 46.5 micrograms per cubic meter. PM 2.5 is a technical metric for fine particulate matter, small enough to penetrate deep into the human respiratory system. This concentration is over 9 times the World Health Organization's recommended safe limit of 5 micrograms. The primary source of this trapped particulate matter is the city's rapidly expanding population of 1.2 million fossil fuel-powered vehicles, crawling through heavily congested streets. The absolute bottleneck of this traffic is the 27-kilometer Kathmandu Ring Road. It acts as the primary transit artery for the entire valley, absorbing the heaviest daily commuting volume. Because the valley's geography physically prevents pollutants from escaping, standard municipal emission controls fail here. Solving this requires a total, systemic overhaul of that central transit artery. The proposed intervention is the electric Metrobus system, or EMBS, built around high-capacity, 100-passenger articulated electric vehicles. The proposal scales this hardware massively. It is a $107.15 million initiative designed to deploy exactly 1,000 of these zero-emission buses directly onto the ring road. Deploying 1,000 buses requires deep infrastructural integration across the city's power and transit networks. This immense project forces the city to couple its public transit network directly to the national energy grid. Success relies on engineering a physical architecture capable of surviving extreme weather, while radically altering the macroeconomic energy dependency of the entire nation. The first major engineering choice for this system is selecting the energy source: battery electric buses, known as BEVs, versus hydrogen fuel cell electric buses, or FCEBs. Hydrogen FCEBs were categorically rejected. Nepal currently lacks domestic hydrogen infrastructure, and the technology is highly vulnerable to the country's intense monsoon humidity. Nepal holds a massive, overriding energetic advantage. The national electricity grid is powered 90% by renewable hydropower, generated by dams like this one. Selecting battery electric buses explicitly leverages the country's existing 1,500 megawatt hydropower surplus. Megawatts measure the volume of electrical power output. This choice cuts foreign fossil fuel supply chains out of the transit equation entirely. Battery electric buses transform the municipal transit system into a direct mechanism for using the country's renewable surplus. The result is a true zero direct CO2 operational footprint. With the energy source selected, the physical vehicles themselves require exact modifications. Off-the-shelf electric buses will fail in Kathmandu's environment. Every vehicle in the fleet must meet an IP67 rating. IP67 is an engineering standard confirming a piece of hardware is completely sealed against dust ingress. This hardware requirement is a direct response to Kathmandu's dry season. Ambient PM 2.5 levels spike to 500 micrograms per cubic meter, choking unprotected mechanical intakes. The second physical challenge is the topography. Navigating Kathmandu requires steep, continuous descents through the hilly terrain. This diagram illustrates how regenerative braking systems solve this. As the bus descends a steep gradient, the motor runs in reverse, capturing kinetic energy and recovering up to 20% of the vehicle's battery power. The vehicle hardware is custom-tailored to transform Kathmandu's environmental liabilities, the thick dust and the steep hills, into managed operational parameters. Running this 1,000 bus fleet requires a daily charging demand of 300 megawatt hours. A megawatt hour is a unit measuring continuous energy output over time, and 300 represents a massive electrical load. This schematic illustrates the Balaju depot. 240 standard 80 kilowatt chargers draw energy overnight. Zooming out to the ring road, a supplementary network of 10 pantograph rapid chargers use overhead arms to deliver a high-speed 150 kilowatt charge in 15 minutes during peak transit hours. The most critical civil engineering threat to this electrical infrastructure is the severe seasonal monsoon flooding. Preventing catastrophic short circuits requires specific infrastructural hardening. All depot foundations must be elevated by 1.5 meters, and physical fire breaks are installed every 5 charging bays to isolate potential battery thermal events. Without this architectural resilience, a single intense monsoon season could physically destroy the entire $107 million transit grid. The stark economic reality of this proposal is the daunting upfront capital expenditure, or CapEx. CapEx refers to the initial money spent to acquire physical assets. To evaluate municipal feasibility over a 10-year horizon, we have to use total cost of ownership, or TCO. TCO calculates both the purchase price and all operating costs over an asset's lifespan. Comparing initial prices, electric buses cost a steep $100,000 per unit versus legacy diesel. But adding 10-year operational expenditure changes the math. Diesel's imported fuel costs stack rapidly. Utilizing local hydropower, electrics operate at 10 cents per kilometer, compared to diesel's 15 cents. Dropping diesel imports entirely saves the city an estimated 1.97 billion Nepalese rupees annually. The EMBS converts high initial capital costs into long-term operational sustainability by abandoning imported fossil fuels. Attempting to deploy all 1,000 buses simultaneously onto an unprepared electrical grid carries a catastrophic risk of overloading the local infrastructure. To mitigate this, the project relies on a strictly paced 36-month, 3-phase deployment strategy. Phase 1 is the pilot. The city deploys just 50 buses to test terrain limitations and climate assumptions in real-world Kathmandu conditions. Phase 2 is expansion. 200 additional buses enter the network only after their required power draw is carefully aligned with completed localized substation upgrades. Phase 3 is full deployment. The remaining 750 buses roll out across the full ring road once the architectural and logistical foundation is proven stable. Deliberate, incremental scaling balances massive electrical grid upgrades with physical vehicle delivery. At the end of the 36 months, the ring road achieves its final projected state. This dashboard tracks the exact environmental returns of the fully integrated system, a 20% total reduction in vehicular emissions, and 43,741 tons of CO2 eliminated annually. Financially, the city captures $22 million annually that was previously hemorrhaged to foreign oil imports. These abstract metrics translate directly into the tangible health and cultural survival of the 6 million residents living within the valley's geological bowl. The EMBS functions as a macroeconomic mechanism, converting locally generated hydropower into mass urban mobility. By combining exact topographical adaptation with strategic grid economics, geographically constrained developing cities can bypass legacy fossil fuel infrastructure entirely to engineer a highly profitable, zero-emission future.